My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I'd like to welcome you all to our International Physics webinar. So good evening to all here in Bangladesh and a very good afternoon to all those who are watching this program live from UK. Today it's our 84th International Physics webinar. So hope you are well and safe from Corona pandemic. All we know that we are staying in a Corona pandemic situation. We cannot continue our normal academic program inside the campus. So we have to start our online program to continue our academic program. I think you have already come to know that our Department of Physics, has started its online program, including online classes and online international physics webinar. And I'm happy to share with you all that we have successfully completed our 83rd international physics webinar. So we are trying to adjust with this new normal situation. So in those international physics webinar, physicists from different countries are coming as a main speaker. They are delivering their speech with our students. They are sharing their knowledge with our students. I think by this way, our students are benefited. Today is a very important day for our department. Today, I'd like to welcome you all to a joint session between the Department of Physics, Pabna, University of Science and Technology, and University of Washington, USA, in a high energy physics. And we have with us here today Dr. Cristiano Alpigiani, postdoctoral scholar, Department of Physics, in University of Washington, USA, and researcher at ATLAS Experiment, CERN, Geneva, Switzerland, and connecting with us from Switzerland through online. And he has already connected with us, so I'd like to welcome our speaker. So good evening and welcome to our International Physics webinar.
Thank you very much.
Thanks for accepting our invitation. So I think you have already come to know the title of our today's International Physics webinar, and title is the Exploring the Lifetime and the Cosmic Frontier. And our speaker is Dr. Cristiano Alpigiani, and postdoctoral scholar, Department of Physics, University of Washington, USA, and researcher at ATLAS Experiment, CERN, Geneva, Switzerland. So it's your time. You can start your session. And thanks again for accepting our International Physics webinar.
Thank you for actually the invitation. Actually, I appreciate it very much. So yeah, in this slide, I want to just give you an idea of basically the work I'm doing. So what is my research, and I'm focusing on what we call long-lived particles. So that's why I'm saying exploring the lifetime and also the cosmic frontiers, because actually I will talk about two different experiments. I'm mainly involved in ATLAS, that is my main experiment at CERN, but I'm also involved in a proposal for a new experiment that is called Matusla, that will explore very, very long-lived particles, but also cosmic ray. So I want to talk about both. But first of all, I want to give you an introduction about long-lived particles. So why we really need long-lived particle? Well, because when we do searches at the LHC, we basically look for, most of the searches like Higgs, SUSY, they look for prompt physics. So physics that is coming directly from interaction point. So what you see in this plot is basically a mass of the particle. We're exploring this very small region close to the collision point, and we don't have basically an idea about the rest. We have a huge phase space that is largely unexplored. And the reason why maybe we are not finding any new sign of the new physics, it might be that simply we are looking in a wrong place. Okay. Now, the nature is plenty of long-lived particles. We know that in the standard model there are many long-lived particles, so it's reasonable to assume, it's not surprising, that also long-lived particles can be present beyond the standard model. So there might be new theory predicting new particles, so new particle might exist, and this new particle might be long-lived. So it's reasonable. But just starting from a very brief slide, focusing on what it makes the lifetime longer. Okay, so just really starting from the basic. So there might be the decay width calculated in quantum field theory might depend on different parameters. So you have the matrix, it depends on different parameters. You have the matrix element, you have small coupling, and all these component can give us a long-lived particle. So you can have a matrix element that can be suppressed due to an approximate symmetry, or there is small effective coupling constant. You might have also very small coupling, that this is actually basically what mostly driven this theory in long-lived particles. Small coupling, long lifetime. But you can also have the phase space that might be suppressed. And all these different possibility to produce long-lived particles, so to extend the lifetime of a particle, leads to many different theory. Okay, so we really have many theory predicted the existence of a long-lived particle. Just two examples regarding the standard model. Also, we might also have an approximate symmetry. We might have a heavy mediator, and this is really one of the things that, for example, drive theory like hidden valley theory. So the idea is simple. You have a dark sector and the standard model. So the standard model is the visible sector that we see, and the dark sector, for example, represented here, is an area that we cannot access because the energy to access it is very big. So we cannot really, at the moment, enter inside, let's say, the dark sector. But there are mediators that make a sort of communication between the standard model, so our sector, and the dark sector. And for example, the Higgs might be a very natural mediator between the dark sector and the standard model. So there are several theories, for example, that predict the existence of this long-lived particle produced by Higgs decay. So the Higgs is a sort of portal between the dark sector and the standard model. And here you see a series of examples of long-lived particle in the standard model. So you have a neutron that have a very long lifetime, let's say 15 minutes, and this is given by the fact that you have a heavy mediator, you have a phase space suppression, and you also have an approximate symmetry, this is isospin, and this gives the neutron a long lifetime. The muon is another example. You have high mass, again, of the W boson, but you also have a small coupling, and this makes the muon long-lived. Okay? The pion, and you have a heavy mediator, again, another example, and also the B quarks, where you have a phase space suppression and approximate symmetry, flavor symmetry. So you see here you have a series of examples in the standard model that gives long-lived particle. Basically, we take this kind of example and we extend to new theory beyond the standard model. And as you can see from this slide, there are many theories that give long-lived particles. This is very complicated, complex slide, but you see that you have many kind of theory, naturalness, and all these BSM beyond the standard model theory predict the existence of long-lived particles. So you have also different kind of, for example, long-lived particle can also explain dark matter and so on, and this is an example. You see here, for example, a list of particles from SUSY, neutron naturalness, dark matter, and portals, where you have what is giving the particle a long-lived lifetime, for example. You see here the different kind. But how much is the lifetime? How much long can be the lifetime? Well, there is a limit on an upper limit on the lifetime, and this is coming from the baryogenesis. The upper limit on the lifetime of the long-lived particle is 0.11 second, so less than 1 second. And the reason is that the baryogenesis from cosmology measurements, from cosmology theory, is very well known. So we really very well known what is the baryogenesis. And if you have a particle, a long-lived particle with a lifetime longer than 1 second, that means that at the beginning of the universe, you will have a particle, long-lived particle produced, and this long-lived particle maybe have a lifetime of 1 minute, for example. Having a so long lifetime, they will basically change the baryogenesis. So the baryogenesis is very well constrained. And so for this reason, we know that long-lived particles cannot have a lifetime higher than 1 second. But this, considering that the particles are traveling at the speed of light, gives a very broad range of lifetime in terms of lifetime that can be reached by a detector, few millimeters up to kilometers. So we have a very broad range of lifetime, even if it's only 1 second. The long-lived particle can also explain dark matter. So there are a variety of dark matter candidates that can really be produced together with long-lived particle. Because of course a long-lived particle cannot be dark matter, because the definition of dark matter is a neutral, stable particle. Okay, but the long-lived particle is not stable. But there are many theories that predict the existence of long-lived particle produced in association with this dark matter. And there are also this theory where you have a really dark sector that are the hidden valley particle that are in communication thanks to this mediator to the standard model. This gives also origin to dark matter particle in the early universe, of course. Now, moving into what is also very interesting from the point of view of the experiment and point of view of the accelerator, that is the long-lived particle phenomenology. Because at the end, we know the theory, okay, it's fine, and we can use the theory to make model, and the model will help us to search for this particle. But from the experimental point of view, we are very interested in what is the phenomenology of the long-lived particle at the Hadron Collider. So how we can really see this long-lived particle in an experiment like ATLAS, CMS, and so on. And certainly the LHC is the most powerful machine that we have at the moment. And there are several searches that also can undoubtedly constrain the, for example, the existence of long-lived particle. We can also do missing energy searches, and these are very crucial in proving new physics. But the problem of the missing energy searches is that you have a very high uncertainty in terms of measuring the missing energy in the detector. So if you are looking for 100 GeV particle, it might be possible to measure them. But if you are looking for a few GeV particle, that is very complicated to constrain using missing energy measurements. So, and then for example, imagine that you have two protons that collide, and this creates a neutral particle, long-lived particle. But the mass of the lifetime of the long-lived particle is very, very long. So it does not decay inside the detector, but it goes away. It's not detected by your detector. So this is seen as a missing energy. So this is seen as a candidate of dark matter, but this is not a candidate of dark matter because it's a long-lived particle that simply is decay outside your detector. So that's why we need to measure this long-lived particle inside the ATLAS and CMS underground detector, but we also need new detector that can go and reach much longer lifetime, because it might be that really long-lived particles have been already produced by the LHC, but we haven't detected them, simply because they basically escape and maybe they were decay, I don't know, 100 meters above the LHC on the surface. And without any detector catching them, that is simply, for us, for a detector, missing energy. But it's wrong missing energy. It's not dark matter. So the problem of the long-lived particle is that you need to decoupling production and decay. Because consider the first model. This is a very simple model of production of long-lived particle. You have a standard model, so two protons that collide. They create standard model, muon, electron, whatever, another, plus a long-lived particle. This is a very simple model. The problem is that to have a very short lifetime, so to have a very long lifetime, of the long-lived particle, you need a very small coupling, okay? But if you have a very small coupling here, it means that when you collide two protons, you have a very, very few long-lived particles produced. Because if the coupling is very small, yes, the long-lived particle has a long lifetime, but the event will be very, 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 very rare. So you will produce in 5 years of collision at the LHC only a few long-lived particles. That's why, from the point of view of the theory, you need to decouple the production from the decay. So basically, you have standard model that produce long-lived particles, and through, for example, portals, so proton-proton collide, produce Higgs, and this Higgs is a portal that produces long-lived particle. In this way, you are decoupling the production, because the two protons produce the Higgs, from the decay, because then the Higgs generate long-lived particle, that then long-lived particle can decay back into standard model particle. So basically, the best sensitivity is achieved really where we have this kind of model where the production and decay have different coupling constant, big for the production and small for the decay, so that you can have a long-lived particle that you can measure. Here I want to just give you an idea what are the main signature, so the main way of measuring long-lived particle. So we had a few years ago a sort of white paper for long-lived particle made by the experiment at the LHC, where we're trying to define what are the simplified model. And these are really, let's say, the basic model that we can use to study long-lived particle. This is, for example, what I was mentioning before, is the Higgs portal, where you have glue-glue fusion that produce the Higgs, and the Higgs that give rise to long-lived particle. And then, of course, you also have vector boson fusion, you also have ZH production, so you have different kind of production. But here you see very simply what are the main models that produce long-lived particle. This is theoretical point of view, but then from the detector point of view, what we see? Well, we see, for example, neutral long-lived particle that might decay into what? Into displaced jet, hadronic jet. So the particle can decay into hadron, B quarks, C quarks. They can decay into tau particle that then can decay leptonically or hadronically. So they can decay into leptons. So you might have vertices, displaced vertices with two leptonic vertices. So basically you have proton-proton that collide. This gives you a long-lived particle. Then at a certain point, it decays into, for example, two muons, two electrons, and so on. If you are looking at the prompt searches, of course, you will miss all these kind of searches. Because if you look at the center of the detector and then a long-lived particle decay behind you, then you don't see it. So we have many signatures in of the detector to long-lived particle. Because another problem that we have is that we don't know what is the lifetime of the long-lived particle. All this theory say the long-lived particle will decay, blah, 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 with a certain coupling, blah, 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 but they don't say anything about the lifetime. So we have this very huge range between few millimeter to kilometer that we have to explore. So it's not easy. Because it will be much easier, of course, if you have a theory that say, okay, the lifetime will be like 1 meter, and then you focus on that part of the detector, and you measure, you try to find this new particle. But this is not what happens. So you have also this free parameter that give you a very broad range of lifetime, and also a very, very broad range of topology. So you can have different kind of decay, and the decay might be different depending on where the particle is. This is just a plot that I will show you later. This is usually how we basically present the results on a long-lived particles. Okay, this is the branching ratio for the production of the long-lived particle versus the lifetime, and this is a sort of U shape or V shape, depending how you want to see, is very, very common in long-lived particle. And this is where it's coming from. So basically, the probability of having a particle that decay inside the detector depend, of course, by a constant that is the Solin angle. Of course, the bigger is the coverage of your detector, the higher is the probability of measuring the long-lived particles. So that simply the coverage. But then you have two terms, okay? One term that basically give you a contribution at smaller lifetime. So drive the efficiency at smaller lifetime. That is this exponential, okay? And then you have another term here that drive the reach of longer lifetime. So for smaller lifetime, it means that you need a very, very high reconstruction efficiency, very close to the point where the proton collide. So in the tracking system of your detector. While for long-lived particle, very, very long-lived particle, you need a detector that is far away. That's why I will say that if you want to explore very, very long-lived particle, you cannot do it with the experiments that are underground. You need additional experiment, like the one that I will mention is on the surface. Because in this way, you can extend this and go and reach longer lifetime. Because this increase when the detector is bigger or more far away. So there are many searches for long-lived particle in the standard, in the LHC detector, so ATLAS, CMS, and LHCb. But you have to consider that all these detector, all these searches are very, very limited. Limited by what? They are limited by the background. A big amount of background, because when you imagine you don't have an electron-positron collider where you have a relatively clean signal. You have a hadron collider. So when you collide two protons, you produce a lot of garbage, okay? A lot of background. And this makes all these searches very, 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 very complicated. And the background are very, very different. You might have a instrumental background. You might have material interaction. That means that basically the same particle that cross your detector will create other particles, shower of other particles that might look like a sort of displaced vertex. Okay? You might have also beam-induced background. So the beam that circulate inside the LHC generate a lot of particles, okay, that can cross your detectors and then can fake your signal. Okay? You might also have cosmic background, cosmic ray that reach the cavern underground and they create also fake vertices. So you need a very powerful all this complicated background. And in some cases, they are very complicated, very complex to model. And we really don't have any simulation. Or we have a simulation, but the simulation is not very reliable. So we have this very big problem with the background. Also because this big detector, honestly, ATLAS CMS, were not designed to study long-lived particle, because a long-lived particle is something that we start studying like 10 years ago. But this detector were designed more than 20 years ago. So these kind of detector are designed to do prompt physics, so to study particle coming from the interaction point. They are not designed to study this long-lived particle. That's why these searches are even more complicated. We need to adapt this detector to this kind of searches. So we need to model very well this background, and we need a very robust rejection of this background, but we need also dedicated triggers. Now, what is a trigger? When we collide protons, we cannot save all the information that we have, okay? Imagine that in the LHC, we collide protons every 25 nanoseconds. So we have 40 million of bunches of protons that collide every second, 40 millions. Now, if you want to save all the data, that will be, in terms of size, 3-4 terabyte of data per second. 3-4 terabyte of data per second. So you can imagine that we cannot really save all this data. We really don't have the space. So that's why inside all this detector, we have a trigger that is a filter, okay? A filter that selects only the particle that we need. So there is a filter for the Higgs boson, there is a filter for dark matter, there is a filter for SUSY, and so on. But if your filter is not included, then the data are lost. Because really, the data that pass the filter are saved, the other one are deleted completely. So if you don't have a certain trigger, a certain filter, you might miss new physics. So this is something that is very important. But I mean, we cannot, of course, live without trigger because we really have a huge amount of particle produced. So we need also dedicated trigger that allow to filter and select only these long-lived particles. So we have many problems, let's say, in the searches for long-lived particles. So let me give you an idea of what are, very briefly, a general overview of what are the searches for long-lived particles at the ATLAS detector. Similar searches are also done at the CMS detector. So this is a map of the CERN accelerator complex. These are the different accelerators that we have at CERN, and this is the LHC, 27 kilometers, okay? On the LHC, we have 4 experiments, ATLAS and CMS, that by the way are the 2 ones that discover the Higgs boson. LHCb, that is doing B physics, so it's studying the particle that contain the B quarks, and this is, for example, very important for doing like matter-antimatter asymmetry, so CP violation, and so on. And we have HELICE. HELICE is the detector, is a Large Hadron Collider experiment. It's a detector that studies the collisions between the heavy ions, okay? Because in the LHC, we accelerate protons, okay? And we do that for most of the time. But we also accelerate the nuclei of lead, made of several protons and several neutrons. The reason for accelerating lead is that because we want to try to produce this state of matter that is called quark-gluon plasma, okay, that it was present at the beginning of the universe. And this experiment was specifically designed to do quark-gluon plasma studies. So let's focus on ATLAS. ATLAS, by the way, is the biggest detector that we have on the LHC, and I mean, it's not a small device because, as you can see here, it's 44 meters times 25 meters. So it's a huge. Just to give you an idea, this is a person compared with the size of the ATLAS detector, and has a weight of 7,000 tons. Okay. Now ATLAS has different sub-detectors to measure the different properties of the particle. We have here silicon tracking system that is used to precisely measure the trajectory of all the particles. So we have a pixel detector, strip detector, and also a gas detector that is called transition radiation tracker. That is made of straw. Is a straw detector that use the transition radiation also to make a sort of but also to do discrimination between, for example, electron and hadrons. Then we have a calorimeter that surrounds the tracking system. We have here electromagnetic calorimeter that measure the energy of electrons and photons, and we have hadronic calorimeters that measure the energy of all the hadrons, so all the particles like proton, B quark, so B jet, and so on. And then we have the muon spectrometers. So ATLAS is a multi-purpose experiment, so it doesn't want to focus on a particular part of the physics program. And then we have 2 magnets. We have a solenoid that surround the tracking system, and a toroid, 8 of these coils that surround the calorimeters that generate the second magnetic field. In this way, with the magnetic field, you can measure the charge and the momentum of the particle. Now, you see that you have a very big detector. So ATLAS detector, but CMS, they already are very good tools to study long-lived particles because they are, in any case, very big. And we have many different searches that cover different parts of the detector. For example, we have searches that are focusing on the ID, on the tracking system, searches that are focusing on the calorimeter, and searches that are focused on the muon spectrometer. All these searches are completely different because the sub-detector is completely different. The background that you get in the detector is completely different, and also the challenge that you have, the resolution and so on are completely different. So we have a variety of analyses that are very, very orthogonal and totally different because they need to face different kind of problem and different kind of background. So just to give you an idea about sort of a few analyses that we have in ATLAS, this is, for example, starting from the more far away detector from the IP, from the muon spectrometer. We have searches for displaced jet in the muon spectrometer. This is very easy. So you have a slice of ATLAS. Basically, you are looking for a long-lived Higgs portal, so a Higgs that produce two long-lived particles, then decay into displaced jet. These are neutral long-lived particles, so basically no signal here, but when the long-lived particle decay, it generates standard model particles, so you have signal. So imagine that you have basically long-lived particle that is produced. This travel across your detector, but this is neutral, does not basically leave any sign of their presence, and then at a certain point, it decay into new particle, standard model, like a muon, jet, whatever. And so basically you say a displaced vertex, what we call a displaced vertex. So a vertex of particle far away from the interaction point. And you might have a pair-produced long-lived particles, so two displaced vertices in the muon spectrometer, but you might also have and this is basically targeting this kind of theory. You see here an example of what is called a scalar portal, where you have a Higgs or a high mass boson that is the mediator between the dark sector and the standard model that is produced by the proton-proton collisions. This scalar portal basically generates two long-lived particles, and these long-lived particles decay into fermions, mostly BB bar, so B-jet, okay? But you also have, for example, SUSY model, like distal SUSY, where you have a production of gluino. The gluino that are basically prompts generate two gluons, and the two gluons gives you two prompt jet, so two jet coming from the interaction point, as represented here, plus a synglino that is the long-lived particle that then gives generate a singlet that decay into gluons again, and these are the displaced jet here, plus a gravitino. But the gravitino carries a very small momentum, so basically we cannot really see the gravitino. This is another idea, another long-lived particle. Or we also have baryogenesis that is very similar to the scalar portal, and this model can explain, for example, the matter-antimatter asymmetry. And so you have this kind of a different phenomenology, and I also reported the link here if you want to have more details about the analysis. And we have fundamental two kind of searches, one looking for two displaced vertices, and one looking for only one displaced vertex. Okay. Just to mention the tools, okay, because I told you before, there are many different kind of analysis with different kind of tools. These are, for example, the tools that are used by the muon spectrometer. So first of all, in the muon spectrometer, what is the main background? The main background is coming from jet produced by the interaction point. The good point of the muon spectrometer is that between the interaction point and the muon spectrometer, you have the calorimeters. Calorimeters are made of lead and iron, so they absorb a lot of particles. So the level of background that you find in the muon spectrometer is much, 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 much lower than the one that you find here. But still have background, but it's much, much lower because it's basically shielded by the calorimeters that you have here. Okay, the long-lived particle, of course, neutral long-lived particle, cross the calorimeter basically without any problem, but the other charged particles are basically absorbed by the calorimeter. So the level of background here is much lower, but not zero. Okay, and you still have the main background is coming from jet produced by normal jet produced by hadron collider. Okay, we have a specialized trigger that is looking for cluster cluster of signals, okay? In this muon spectrometer, we use a RPC, resistive plate chamber, to trigger the muons produced by the proton-proton collisions. And these RPC are segmented, okay? When, of course, you have muons, the muons will only hit one part of the RPC. So we only generate one, let's say, point, right? But if you have a decay in the muon spectrometer of the long-lived particle, you will have a lot of activity. And this means that we'll turn on different points of the chamber of the RPC, generating a cluster, let's say, of points. And this is a sign of the presence of a decay of a long-lived particle. So the trigger that we use to select the long-lived particle decay in the muon spectrometer is based on this, okay? If you have a muon, of course, you only have one cluster. But if you have a 3-4 cluster, it cannot be a muon. Well, it could be, but the probability is very, very small. So it might be a long-lived particle. So this is a way that we use to trigger, for example, in the muon spectrometer. But then how do we reconstruct the particles, the vertices? Well, we have another detector in the muon spectrometer. We have RPC, that are very fast gas detector that are used for triggering. But we also have the MDT drift tube. These are detectors that are made of many tubes, okay, that contain inside argon. At the center of the tube, there is a small wire, and this is based on a simple ionization system. So you have an electric field inside. When a particle crosses the pipe, it will ionize the gas, creating free electrons that then migrate to the wire, and so you have a signal. And so when the long-lived particle decay, you will have a lot of heat, a lot of activity in the muon spectrometer coming from the muon, the MDT, okay? And we have a specialized algorithm that is used to reconstruct the segmented track here in the muon spectrometer and then make a vertex. So connecting all these tracks that we reconstruct, we see if all the tracks are coming from different points, then it's not a vertex. But if all the tracks that we reconstruct are coming from the same point, this is a candidate long-lived particle decay. Okay. So here I have the results, that just to show very briefly. I told you that we have the two analyses, and you see that this is exactly the plot that I will show you before, right? So we have the results, branching ratios versus lifetime for the Scala-Porter, baryogenesis, and Stal-Susi. And you see that the shape is what I was mentioning before. Here is driven by the tracking system, so but this cannot be reached by the muon spectrometer, and this is reached. This is the muon spectrometer. If you compare the same search done in the ID, you will get a curve like this. Why? Because the ID is closer to the proton-proton interaction point, so that means that you can cover more the shorter lifetime, but you will not be able to cover the long lifetime. Okay, and then it will also be not so deep in terms of branching ratio. It will be probably like this, because the level of background is much, much higher in the ID. And so this will reduce the sensitivity of your signal. While the lower is the background, the higher is the sensitivity reached in terms of branching ratio. This is another search, similar model like this that I mentioned here. So the X scalar portal, but is looking for long-lived particle decay in the muon spectrometer. In the calorimeter, in the hadronic calorimeter of the LHC, the ATLAS detector. In this case, you have a different kind of detector. So you have a different timing that you don't have, for example, in the muon spectrometer. So you might have different kind of searches. Okay, and so the strategy that you do is different. And for example, in this case, you have more contribution to the background coming from the beam-induced background with respect to what was present in the muon spectrometer, and more background coming from QCD, for example. And this again, I want to summarize the results, and you see the same kind of shape. But if you compare this with this, you will see that the muon spectrometer can go at longer lifetime with respect to the calorimeter. Okay. And then also, just to mention, we also have searches for example, heavy neutron lepton, HNL. This is, I want to mention this because this is a very sort of hot topic of the moment, because now we have many searches that look for heavy neutron leptons. Okay, this may also be very important because for neutrino masses especially, but also matter and antimatter asymmetry. So this is simple, a W that create a prompt muons or electrons plus a neutral particle, that is what we call heavy neutron leptons, that then decay into a muon plus a Z, that then decay the Z, again, can decay into a lepton, of course, and also to hadron. Okay, I just wanted, again, to mention this because it's a hot topic of the moment, and we have two kind of searches in this case for heavy neutron lepton, the prompt, so the long-lived, but also the long-lived version of this. And this is the result for the prompt searches. Sorry, I saw that actually there are Pretam, there are questions. What I do? I see some.
We can discuss later.
Okay.
We can discuss later.
Okay, great. So let me come back. So let me move to the other experiment now, because I told you that the LLC detector, as you can see from the previous slide, can do a very nice job in terms of searching for long-lived particles, but then they are limited by a lot of background. So we need definitely to really reach the frontiers of the lifetime. We really need a background that is free, a detector that is free from background and with no trigger limitation. That's the idea behind Methuselah, that this is the name remembering Methuselah, the longest man that ever lived on the world. So the idea of this detector is very simple, okay? Imagine this is the CMS detector. So here is the point where the proton collide. This is the CMS underground detector. We place the detector far away from the point where the proton collide, on the surface, around 100 meters from the interaction point. Okay, this is a big detector, 100 meters times 100 meters. Why? Because the higher is the distance from the interaction point, the bigger should be the detector, because I told you before, the formula depends on also the solid angle. Okay, so the more distant is the detector, the smaller is the solid angle. So to increase the solid angle, you need to increase the size of the detector. But the idea is simple. You have a big detector with 25 meter high decay volume. So you have a huge decay volume, okay? A long-lived particle is produced by the collision of proton, travel across 1 meter of force, and decay inside the decay volume. So you have a floor detectors, 2 layers that veto charged particle coming from the LLC, because LLC can produce long-lived particle, but it can also produce muons that can travel across 100 meters of rocks. So if you put a detector here, of course the muon are charged particles, so you can veto them, but the neutral particle will be not measured. So a signal is no signal from the floor detector and particle measured by the tracking system, because the long-lived particle neutral cross the detector, decay, create a spray of particles, then particles that are measured by the multi-layer tracking system that is on the top. Okay. For the detector, at the moment we are considering both RPC, so resistive plate chamber, and extruded scintillators coupled to silicon photomultiplier. And even if basically we are moving more on the extruded scintillator because it's easier with respect to the RPC, and they have a timing resolution that is very close. Okay? So this is a very simple idea. And Methuselah can cover several models, because we can go searches for long-lived particle into displaced jet, search for long-lived particle into leptons, and so on. And this is what I was mentioning before. This is what we can gain having a detector far away from the interaction point. This is, for example, the curve that we get from ATLAS, okay? And this is the curve that we can get from Methuselah. So there is a shift down due to the fact that the detector is 100 meter shielded by the QCD produced by the proton-proton collisions. So basically is term of LHC background free. And then you have a long distance from the interaction point that allow to reach the Big Bang nucleosynthesis limit. That ATLAS and CMS cannot do because they are limited by the size of the detector. So there are many models that can be covered, and also having neutral leptons. And of course, you don't have basically background, QCD background coming from the LHC, but you still have some background in the detector. You have a lot of cosmic rays that, in any case, they can be rejected. You have muons coming from the LHC, but this muon coming from the LHC, as I told you before, they can be vetoed using the floor layer, because it's a charged particle. So when you see a charged signal coming from pointing to the direction of the LHC, then you reject it. But you might also have some more problematic background, like, for example, scattering of neutrinos. So you have neutrino coming from the LHC that then create some scattering, then create some particles that are detected by the tracking system. So this is basically like a signal, because the neutrino, of course, is not measured by the bottom layer. Then it generates this activity that is measured by the tracking system. And then you also have a scattering from atmospheric neutrino. But these are kind of background that are basically very, very rare. And in any case, the kind of background they will produce not high beta particle, but they will probably produce particle with a very low momentum that can be easily rejected using time of flight measurement, because this kind of detector can measure the track, but also has timing information. So you can also do a sort of 4D measurement. So you can measure the trajectory, but also measuring the timing. And this will be very important to reject this kind of background. And these are the main ones. Basically, the main one are muons and cosmic rays. So the detector was the idea was detector was like developed 5-6 years ago, and there are many theorists that contribute also to the white paper. There are many studies ongoing about the background and try to estimate what is the background that we expect in the Methuselah. It's relatively clear what is the background coming from the cosmic muons, because I mean, we have several cosmic muon experiments that measure, so we know the flux that is expected. But what was not clear is what is the background coming from the LHC. So we have many models, also simulation, but the simulation need also some real data. That's why we decided to build what we call a test stand 3 years ago. It's not a prototype, but it's something that resembles Methuselah. So basically you have a bottom layer made of scintillators and a top layer made of other scintillators, and these are used for triggering and for vetoing. And then you have 3 stations of RPC detector that are used for the tracking, okay? The idea was to try to understand what was the background coming from the LHC, okay? This test stand was installed, and you see a picture here, above ATLAS. Above ATLAS, on the surface, there is a big space that is empty when the LHC is running. So we place the detector here, and you see here the position exactly on the position. And then we study the background. We measure the track that were crossing the test stand with the beam on and off to separate, for example, cosmic muon from muon coming from the LHC. The results are relatively new, so were really published basically a couple of months ago. And here is basically just a few plots that show you the distribution of downward track, so track going down, versus the zenith angle compared to the simulation from cosmic rays. This basically shows you that we are simulating the cosmic ray very well, okay? The reason why the zenith angle is peak here and not in zero, this is basically given by the fact that we have this, this is given by the geometry of Methuselah that give this kind of the acceptance of the track that you have inside the Methuselah. So that's why. Then we have also the upward track with no beams. Now, you might say, but if there is no beam, why you have upward tracks? Yeah, that was a surprise. We were expecting basically no track when the beam was off, but we found track. And what is this? Well, it's simply coming, as you can see, because the distribution here is exactly at the same shape of the cosmic ray. So these are basically cosmic ray that hit the floor, and then like they are reflected, or you also have a sort of fixed target. So cosmic ray hit the floor and that generate particle going up. So these are upward particle generated by backscattering of cosmic ray. So this is something that we were not expecting, actually was like at this level. And this is the final plot that show the upward downward track and the upward track with beam. Okay, this is real particles coming from the proton-proton collision compared to the IP simulation that we have. So you see that the simulation that we did match very well with what we measured. And again, the reason why is not peak at zero, this is because the test end is not exactly above the IP, but is slightly shifted. That's why this peak is not here, but is here. Okay, so this was a nice measurement. But that's just a few words about really the detector technology. So there is also some work that has been done with the civil engineer to build a Methuselah detector above the surface on the CMS detector. So, of course, it will not be possible to build a modular detector, monolithic detector of 100 meter times 100 meter, but what we will do, we will build a modular detector. So, small module that you see the tracking layer, the decay volume, the top tracking layers, they have a size of more or less 9 meters times 9 meters times 30 meters. And this will be assembled and posed inside a building. So you have here the building on the surface. You see here the CMS site. Here you have the beam line that is 100 meters underground, and this is the detector area, the detector building, where you have the different modules that are installed inside. And about the technology, just a few words if you are curious. So we were thinking to use the RPCs. The reason for using RPC is that a good timing spatial resolution, and they have very small cost. But the problem is that they require high voltage, and the gas is, has a high global warming potential, so we need to move to another gas. We can use the same that is used now in ATLAS and CMS. It's also very sensitive to the temperature, while the scintillator are relatively cheap because we have this extruded scintillator produced by Fermilab. They are very cheap. They can operate at low voltage, so silicon photon multiplier operate at a much lower voltage. They don't have any gas, no problem with thermal stability like for RPC. So this is a good solution that we are considering, especially because they have a very nice timing resolution. And just if you're curious, I will also show you the extruded scintillator facility that is at Fermilab, and they can produce a lot of scintillator, and this scintillator are being used already by neutrino experiment like mu2e, okay, T. So it's very nice. But the last thing that I want to mention is that let's go to the side of the cosmic frontiers, is that, okay, we have a detector that is placed on the surface, so no QCD background. We have a lot of cosmic ray muon that is background, but we can use this cosmic ray muon to do also physics. I mean, this is really something that we can do with this big detector. And this is really a guaranteed return on the investment, because if you build a detector to study long-lived particle and then you don't find any long-lived particle because they cannot be produced maybe by the LHC because the mass of the long-lived particle is too high, so we need a new accelerator, 100 kilometers, something like that. Instead, if you do searches for cosmic muons, of course you can do physics, you can do results, because in any case there are many studies that we need to do. And it's something that is really will return certainly some results. And I just want to try to summarize here. So Cascade is one of the main experiments that was one of the main experiment competitor, let's say, with the Methuselah measurement. But Cascade has a bigger area. But the difference with Methuselah is that Methuselah has almost 100% coverage. So you have all these detectors like Auger and so on. They have a big extension, but they have all this block of detector spread around. They don't have a full coverage. While this, here you have a full coverage. And Methuselah can also work in two different ways. Standalone, measuring only cosmic ray alone, but it can also be synchronized with the detector underground. And this is very, very important to study, for example, muon bundle. And what Methuselah can do is basically explore this region between the knee, the first knee and the second knee. This is a very important region because this is basically the point where you have a principle, the transition between galactic and extragalactic cosmic rays. And this is an area where you really have a sort of a tension, because if you zoom a little bit here, you see that here you have many experiments, but you see that many experiments show very different results. And some of them are in agreement, some others are in agreement among themselves, but in any case, there are a group of experiments that show very different results. I'm not a cosmic ray expert, but in any case, they told me that this area is very, very interesting, also because the full coverage of Methuselah will also allow to lower the energy threshold. So this will allow also the comparison with satellite measurement, like CREAM. This is very important because we don't have the same comparison with the CREAM and other detectors that are on the surface. And it will also be important, for example, if you want to, for example, extend the life, the reach also above the second knee. I mean, now at the moment we are considering only scintillators to measure the cosmic rays, but if you introduce also a layer of RPC, because of the scintillator you are only digital readout, but you also have an analog readout with the RPC. I mean, digital readout means that if you have a scintillator bus, because at the moment you are considering a scintillator bus of 5 meters. Of course, if you have a shower of particle, that will saturate the scintillator. While if you have the RPC, you also have a charge measurement, you also have an analog measurement, and you can also, when you have this kind of shower of particle, shower of cosmic ray, you might also have an additional measurement. So this is just a simulation that we have done, trying to measure air shower, extensive air shower created by cosmic ray for using only scintillators. And we can really do very nice measurement, already considering like a 4 centimeter wide bar times 5 meters of extruded scintillators. But if you think to extend also add an additional layer of RPC, that will be very, very important, because it will allow introducing also digital readout to improve a lot the measurement above the knee. And that will be also very, very important for vertical air shower, because with the scintillator you can also study very inclined air shower. You don't have a very high resolution for a vertical because everything is saturated. While if you have also a layer RPC, you can also improve the measurement of the vertical air shower. And this multi-message astronomy is something that is very, very, very important. Oh, sorry, that was supposed to be my summary and conclusion, but I think that something happened. Sorry, I didn't realize that. Anyway, yeah, so my summary was simply that, yeah, so, well, first of all, thank again for the invitation. And I think the study of long-lived particle is a very, very nice field, because it's really, we started a few years ago. It's gaining really a lot of people working on this. We are getting a lot of people. It's very interesting. We are not covering a lot of phase space, so there is really plenty of potential for discovery. And also with the new experiment that we are planning to have at CERN, if approved, we will also be able to further extend the search's very, very, very long lifetime. But also, just to show you the complementarity of the search that we do at CERN, we can also try to think to go to the cosmic ray. This is something that the CERN has not explored yet, and can maybe do this using the Methuselah experiment. Okay. Thank you.
Thank you.
I hope it was clear.
It was a very wonderful session with you. So I think students have learned a lot of things about the lifelong particle and cosmic frontier. So if you allow, we can start our discussion. We have got some question in inbox and also comments. So first I'll go in inbox. So what are the candidates for dark matter?
What are you mean the candidate?
Yeah.
Well, there are. Well, certainly the main candidate of dark matter is the neutralino. The neutralino is the most stable, the stable SUSY particle, the lighter stable SUSY particle, and basically this is a neutral particle, is very massive and is stable, and this is exactly what we want for a dark matter. But in any case, there are many other kind of particles that, yeah. So basically, everything that is stable, neutral, and heavy, it can be considered dark matter. So yeah.
Okay, thank you. So what will happen when the dark matter particle interact with standard model particle?
Well, yeah, I don't think I have anything about that. Yeah, you can have well, there are different ways of basically study dark matter, and a free way basically. One is to produce it at the LHC. Another one is the dark matter annihilation. So basically, this is what, for example, AMS detector on the ISS is doing. So dark matter annihilate with other dark matter, and create, for example, electron and positron. Otherwise, you can also have the recoil measurements. So this is exactly what happened when dark matter hit particles. There are many searches, for example, also in Italy, in Gran Sasso, the laboratory, that really look at the recoil of dark matter to nuclei. So a dark matter basically hit a nuclei, and the nuclei recoil as a recoil, and then measuring this recoil, you can constrain, have information about the dark matter that generated. So like basically it does the same like a ball that hit another ball. This is one of the ways that we use to study dark matter. That is very, very complicated because, of course, you have a lot of background. But yeah.
Thank you. So we have another question in comments. So could the LHC help us to look for extra dimension of space-time?
Yeah, I mean, in principle, there are many theories that also are connected to this extra dimension, like, for example, Kaluza-Klein theory. So in principle, well, at the moment, I think we are exploring probably much lower energy. But, I mean, in principle, yes. I mean, if you have a theory that say also there is this discussion about the gravity, why the gravity is so weak, it might be that simply we are see one dimension of the gravity, so, and that's why in our dimension the gravity is so weak, but then if you sum up all the other dimensions, that will not be so weak. So yeah, I mean, there are several theories that predict the extra dimension, of course, and we can, if they are can be reached by the LHC energy, we can probably try to study. Of course, I don't think we can really see the dimension, but what we can see a particle produced, maybe. I don't know if I don't know. I'm not a theoretical physicist, so I'm not sure. But I would say yes. Yeah. Okay. Can you hear me? Oh no.
So sorry for the technical problem.
Can you hear me?
Yeah, I can hear you.
Okay,
so this may be the last.
Okay.
Yeah. There may be the technical problem. Sorry. So this may be the last question in the inbox. So what is the baryogenesis? You have already maybe talked in your presentation. So
yeah, basically, that's basically the sort of a theory. So is a theory that basically predict the existence of long-lived particles, and instead of a long-lived particle decay into like a particle antiparticle, you generate basically an asymmetry between the lepton and the hadron, and asymmetry between the charge. So basically, that could explain what happened at the beginning of the universe. So why, for example, we have more matter than antimatter. And this is one of the way of explaining. So basically that there was this long-lived particle, and you have basically more matter that was produced with respect to antimatter.
So thank you for accepting our invitation. We would like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology. Today maybe your third talk with us. So two of them are from conference organized by CERN, and this is our International Physics webinar. So thanks for accepting our invitation, and so I think our students have learned a lot of things by your lecture, and so hopefully in near future we will arrange another webinar with you, and after the COVID we will definitely invite you in our university for a face-to-face session. So thanks again. Bye for today.
Thank you.
See you.